MAP4C 5.5 exponential models. We're going to investigate exponential models in the form of tables, graphs, and equations. A table of values represents an exponential relation if the ratio of each pair of adjacent points are equal. For example, do the table of values represent exponential relations? So when we compare our two variables, our x, or independent variable, should be increasing by regular intervals. And then we can compare adjacent y values, but instead of using first differences to determine whether or not it's linear or nonlinear, or second differences to determine whether or not it's quadratic or non-quadratic, we will investigate the ratio. So here, the ratio of 64 divided by 51.2, this is equal to 1.25. And 80 divided by 64, which is 1.25. 100 divided by 80 is 1.25. So the growth factor is constant. The relationship is exponential. Next, in our second example, the x intervals are regular and the y intervals, when we take ratios of adjacent points, 25 divided by 35 is 0.71, 15 divided by 25 is 0.6, and 5 divided by 15 is 0.33. So, the decay factor is not constant. The relationship is not exponential. The equation of an exponential relation has the variable x as the exponent. So that is the key characteristic. Remember that a and b are constants, meaning they're actually numerical values, where a is the initial value. So it can be interpreted as the y-intercept, and b is the growth factor, the rate at which it's increasing or decreasing. So if we have the following, which equations represent exponential relations? When we look at this equation, the variable x is the exponent, and that is a key characteristic of an exponential relation. The second example, 10x squared, this is non-exponential. The variable x is not the exponent, and it's the base in this case. And this is a degree 2 polynomial. We should be able to identify this as a quadratic relation. We're going to compare pairs of exponential relations. For example, two colonies of bacteria each start with 100 bacteria. The population of colony A doubles every hour, and the population of colony B triples every hour. So write an equation to model the population of each bacteria colony. So we said earlier that A is the initial value, and for each case it's starting with 100. So A for each equation will be equal to 100. But B is the growth factor. And colony A doubles, so we can express that as the following. If it's doubling, this is the growth factor. And remember that exponents are used to express repeated multiplication. So for every hour, which is x, we multiply the population by 2. That's doubling. And for colony B, the population is tripling. So 3 is the growth factor, and our initial value is still 100. Next, it says to graph each equation on the same screen. So you can graph these by coming up with a table of values, substituting into the equation, and generating all of the ordered pairs that you can use for maybe each hour. We will later investigate how to use spreadsheet software to be able to graph this data. Looking at the graphs, colony A is significantly slower than colony B in its rate of growth. So remember, it's as a percentage growth, this is 300% versus 200%. Next, graphs of exponential functions. The graph of an exponential relation is a curve with a horizontal asymptote. So a horizontal asymptote is a line that the graph is approaching but not actually touching. And same thing here on the x-axis, there is a horizontal asymptote. So the way to think about this, I will use the example of exponential decay. If you had a population that was maybe becoming half after a certain period of time, then let's say after every day it becomes half, and each and every single day half of the existing amount is remaining. So as far as time goes on, you can picture going on infinitely, there's always half of the remaining material that would still exist, and therefore it never actually becomes the value 0. It's approaching but not actually equal to the value of 0. Now, to identify when we have exponential growth versus exponential decay, what we need to pay attention to is b, the growth or decay factor. So if b is greater than 1, we would end up with a graph that looks like this, opening up to the right. It causes growth. And this can be understood as when we need to multiply by something that is greater than 1, it makes a number larger. For example, when you're calculating sales tax, we can multiply the subtotal by 1.13 because 1 times a number gives you that value back. 1 times anything is itself. But that additional 0.13 represents the HST, or a 13% increase. So we'd expect that anytime we have a number greater than 1, we see an increase in the image or the value. On the opposite end, exponential decay, whenever b is between 0 and 1, our growth factor, we expect to see exponential decay. I'll use half as an example. If as we progress there's a half, a quarter, 1/8, 1/16, 1/32, and so on, we're getting a smaller and smaller value as we take half of the amount and repeat that calculation, or repeated multiplication by a half. The value would get smaller and smaller. And that's what we see happening here as x increases. The value is getting smaller and smaller. So this should help identify the different ways in which we can have exponential models.